Good morning everyone. Today we are going to discuss our project which is based on designing a computer based processor. RISC-V is a open source instruction set architecture which allows flexible, customizable and cost effective processor. Our problem statement is, as you can see, the problem we are addressing is the need to design and implement a 32-bit RISC-V processor that is both functionally correct and physically realizable. We aim to design in two architectures, which are single cycle and pipeline, which is 5-stage multi-cycle. Single cycle is where each instruction completes in one cycle, one clock cycle, offering simplicity but limited performance. Whereas pipeline is which breaks instruction execution into multiple stages to improve the performance and throughput. Functionality using Xilinx method and then take the design to the parent RTL to GDSI flow for the complete physical realization, preparing for potential fabrication. The objective of this project is to design and implement a 32-bit RISC-V processor in both single cycle and pipeline architecture. And the second point is to functionally verify the processor using simulation tools like Nevada. The third point is creating hands-on experience with RTL design, hazard handling, and coding mechanics. Third point is to perform the physical design using CAD tools, using the design from RTL to GDSI, and to analyze the performance, the efficiency of the single cycle versus pipeline architecture, understanding the trade-offs in complexity, speed, resource utilization, etc. Thank you.
Good afternoon, sir. Today I am going to talk about the methodology. First one is requirement analysis and specifications. What are the requirements needed for our projects and what are specifications we required for our project. Next step is design and RTL development. After requirements and specification, we move to the design process. We design the Verilog code and simulate it in the divider using divider in where RTL development takes place. Next one is verification and simulation. We enter the Verilog code and we done the verification through the divider. We check the output if expected output is complete. And simulation was done also using graph. After simulation, we generated a graph which shows the output. What are the inputs we are given? If the outputs are expected, output is correct as expected or not. Next one is synthesis and backend flow. Synthesis is not needed to generate the netlist. It's the second step of output where netlist is the user to input as an hardware for PD design, physical design, where synthesis can be done. It will generate the netlist and backend flow. We use it ASIC backend flow. I am going to show the ASIC backend flow. First, we generated the netlist. After getting the netlist, we move to the floor plan. After moving to the floor plan, next we go to the placements. After placements, we go to the continuous time survey, where we check the graphs and routing also is explained. Next step is routing. And the final step, next step is sign off. After this, the GDS2 file is generated. Netlist, which is the output in the divider. First we get the netlist as the output. Next, after getting the netlist, we move to the floor plan, where we plan for floor plan is for some metals or some resistors or transistor. What are the size of the floor plan required for the component. After floor planning, we move to the placement. Where the metal where the polysilicon layer should be placed. All we discussed, all we done through the placements. Next is continuous time survey, where we check the continuous clock for if our design or placement is good or not. After doing continuous time survey, we move to the routing, where routing takes place when connecting metal to metal or metal to polysilicon, etc. Then sign off condition, then GDS file will be generated after DRC and LBC check only. Next step is performance evaluation and comparison. Where performance evaluation means we evaluate performance using the parameters analysis and we compare parameters like time, area, power of single cycle. And comparison means after doing the five stages of pipeline, we compare single stage and 5 stages also. Comparing both single stage and 5 stages using area, power and time, we compare which is better or which is efficient, which is more used, etc. The last process is documentation and reporting. After completion of our overall project, we create a documentation of complete procedure what we have done in this project and reporting to after documentation we do reporting, because if someone need our projects to use further processing in future, the reporting helps them to guide them through the project. Next, we move on to the tool survey. First tool we have used is Vivad for RTI simulation and verification. As explained before, RTI simulation is simulating the regular code and verifying through the expected output. What is the expected output we want to know, and we are getting the output or not. We go through the Vivad only. And key features in RTI simulation, what we do the simulation process, we get the waveform, we do waveform analysis and we write a test bed for required code and verify through giving the inputs and receiving the outputs, and FPGA synthesis support. And means after getting the expected waveform and output, we simulate our code through the FPGA gate to check we are expecting we are getting expected outcome or not. Next tool is cadence genus or RTL compiler, which is used for synthesis process. After getting the netlist and in the simulation process, we are going to the synthesis process where it converts RTL to gate level netlist. We have RTL code, it converts to gate level netlist, and we do timing analysis and area estimation. Timing analysis means what type of clock pulses it takes, what type of clock pulses it takes, and area estimation, what are the area required for certain metals, etc. Next, cadence nodes. Place and route takes place where we place some metals, polysilicon layer, etc. and route them by connecting through wires. Fourth line placement, key features in this fourth line placement, routing, timing closure, DRC and LBC. DRC, design rule check, which is ensures the physical layout of chip follows the manufacturing rules. Means we are designing the physical layout of the chip follows the manufacturing rules given by the semiconductor foundry in some company, which cadence company, etc. We are matching that rule or not. It will check design rule check that process. Example like minimum width of metal wires, minimum spacing between two wires, wire contact size, etc. Next, we go to the LBC, where layout process schematic. It checks that we have designed one schematic in first process, and next we go to the layout. It checks both the layout and schematic are same or not, and it also evaluates our input. We want the input schema and we getting the outputs are correct or not. We will check in the layout schematic. Next, fourth tool is RISC-V GCC toolchain, which is not yet used in our project. It will be used in phase 2 while designing the 5 stages pipeline. It is used for assembler and compiler. Key features include compile test programs for RV32I, generate machine code for verification, waveform viewer, which is also not used in our projects now. It will be used in phase 2. Waveform analysis after getting 5 stages pipeline out output waveforms, we will visualize the waveforms, visualize signal transitions and pipeline stages and hazard detections. In 5 stages, we face the problem like hazards, control hazards, data hazards, and another hazards, etc. So overcome that hazard problems, use hazard detection also. Thank you.
Sir, today I will be explaining the single cycle RISC-V processor data path. As the name suggests, in a single cycle design, each instruction is fetched, decoded, executed, memory accessed, and written back all within one clock cycle. I will walk you through each block of the data path and then explain how they all work together step by step. So the first block is program counter. So let's start with the program counter. The PC is a special register that always holds the address of the instruction that the processor needs to execute next. Normally, it just increments by 4 because each RISC-V instruction is 32 bits long, that is 4 bytes. But in case a branch or jump instruction, the PC can also load a target address. So in short, the PC ensures the processor always knows which instruction to execute next. The next block that comes is instruction memory. Once the PC provides an address, the instruction memory outputs the instruction stored at the address. The instruction contains different fields such as output code, which tells the type of instruction, RD, the destination register, RS1 and RS2, the source registers. There are also immediate field, which provides the constraints and offsets. This stage is called instruction fetch stage. The next block that comes is control unit. Now the instruction goes to the control unit. This block is like the brain of the data path. It decodes the instruction fields and generates a set of control signals. These signals decide how data should flow through the processor. For example, reg-writer decides whether we write into the register file. Mem-write decides whether we store into memory. Result source decides whether the value written back to the registers comes from the ALU, from memory, or from PC plus 4. And so the control units makes sure the data path behaves correctly for each instruction. So the next block that comes is register file. RISC-V has 32 general purpose register. The register X0 is always 0. This block can read two registers at the same time and write it into one register. This block is crucial because registers are much faster than memory and most operations happen directly between registers. So the next block that comes is immediate generator. Some instructions use immediate values like constants or offsets. That's where the immediate generator comes in. It extracts and sign extends the immediate field from the instruction 32-bit value. This is needed for load, store, branch and jump instruction. The next block, which is a very important block that comes is ALU, Arithmetic Logic Unit. It is the workhorse of the processor. It takes two inputs. The first is usually a register value from the register file. The second can either be in the register value or an immediate based on the control signal from ALU source. The ALU can perform many operations. The operations which generally are performed by the ALU are arithmetic, that is addition subtraction, logical and or XOR, shifts, left shift, right shift. It produces two outputs, ALU result, which can be used as a final result or as a memory address, the zero flag, which is useful for branch decisions in the BUQ or BNU. The next block is data memory. After the ALU, if the instruction is a load or store, the data path uses data memory. For a store instruction, the ALU results acts as the memory address and the data from register is written into memory. For a load instruction, the ALU result is again the memory address and the value from each is read and sent back to the processor. This is controlled by the memory write and result source signals. So the next block that comes is multiplexers, which are also known as MUX. These are like traffic controllers inside the data path. They decide which input should be passed forward. Some important muxes are result source mux, source mux, and PC source mux. Without muxes, the data path wouldn't know which data to use at each stage. So the final block that comes is adders. There are also two adders in the data path. One adds 4 to the PC for normal instruction sequencing. The other computes the branch target address by adding the PC with extended immediate. These allow both normal execution and control flow changes. Execution flow. This is the I will be explaining the execution flow in a very brief manner. First instruction is fetch. The PC fetches the instruction from instruction memory. Then comes the decode. Then comes the execute. Then comes the memory access. After that, write back will come. At last, update PC. All of this happens in a single clock cycle. Explain an example. So let's take an example instruction. Load x5 8x2. This PC fetches the instruction. The PC fetches the instruction. The control unit recognizes it as a load instruction. Register file provides the value of x2. Immediate generator. Uh, what the next block is immediate generator provides 8. ALU adds x2 and 8 to compute the memory address. Data memory reads the value at the address. The result is written into register x5. Meanwhile, the PC moves to the next instruction at PC plus 4. So in one cycle, a complete load is executed. So I will, to conclude, the single cycle RISC-V data path is simple but powerful. The PC and instruction memory handle instruction fetching. The control unit, register file, and immediate generator handle decoding. The ALU and address handle execution. The data memory and the muxes handle memory, operations, and data flow. Finally, everything comes together in the right backstage. This design is great for understanding the basics of RISC-V through in my practical multi-cycle or pipeline processor are much more efficient. Thank you.
Hello, good afternoon. Today I am going to explain about the simulation survey of our major project, the implementation of RISC-V architecture and design. So in this simulation survey, we have reported two reports. So the report number one is ASIC design and the report number two is RISC-V processor engineering log. So the report number one ASIC design is done by the author Harish and Bola, and he is done complete backend design of the and he used the frequency of 115.5 gigahertz. So this is the major thing we want to notice, and we also done the DPRs and NBC check and GDS2. And the report number 2 is completely about the design. So this is the major part which we have done in this phase 1. So in this design part we have used Vivado as a tool, and we have implemented each and every blocks using Verilog code. So here he has done 5-stage pipeline. So initially we have not started with the 5-stage. We have only done single stage pipeline cycle. Now I am going to explain about the expected output and the results which we have been implemented. So initially what we have done is that we use the tool Vivado. In that Vivado we done each and every block using the design file. So we have wrote the design of the each and every block, and the same for the same design file we have wrote the test bench. So using this design and test, we have checked the performance, area, and power, how it has been utilized. So each and every block we compared each and every block POP values. So then we started the RTL simulation. So in that simulation we checked whether the output which we expected was correct or not. So this is what we have done. So and next GDS2 layout. So this will be continued in the phase 2. So we have not done. We have done only the front end part and area, time, and power reports. So these reports will be compared by using the pipeline design. So initially we started with the single cycle. Then we will start with the pipeline architecture of the RISC-V processor. For pipeline we have 5 stages like instruction fetch, decode, and execute, and memory access and write back. So in these 5 stages we are trying to implement using the putting into the latches in between and designing the thing. And understanding is that the layout part. So we are trying to implement only the ALU unit in the layout. So the pipeline architecture and CAD tools, we use only 2 tools. The first tool is that Vivado, and the second tool is the
Good morning everyone. Now we are going to discuss the references which we have used for the project. The first one is RISC-V reader. It's a book written by uh, David and Andrew Waterman. This book is one of the most fundamental references for our project. It introduces the RISC-V instruction set architecture in a very clear and concise way, making it easier to understand the basics of instruction formats, operations, and philosophy behind RISC-V. Since our project involves designing the processor that follows this open source ISA, this book acted as a starting point for learning the structure and implementation details of the RISC-V instructions. The second one is Digital Design and Computer Architecture by David Harris and Sarah Harris. This textbook, this textbook was essential in bridging the gap between theoretical knowledge and practical processor design. It explains in details how data paths and control logics were built, which is exactly what we need for the implementing both single cycle and pipeline processor architecture. These concepts of instruction execution stages, memory interactions, and control signal described in this book guided us in structuring the data path and designing the processor in modular way. The third one is RISC-V Instruction Set Manual by Waterman and Patterson. This paper was published in 2011. Uh, it defines every instructions, its encoding, its operational behavior, and extensions available. Whenever we had to design or verify instruction execution in our processor, we directly refer to this manual. In short, it ensures that our design remains fully compliant with the RISC-V standard. The fourth one is design and implementation of 32-bit single-cycle RISC-V processor on FPGA. This research paper provided us with the practical references that was very close to our project objective. It describes how a 32-bit single-cycle RISC-V processor can be designed and tested on FPGA hardware. The fifth one is RISC-V foundation of website. This official RISC-V website is the most updated and authoritative source for everything related to RISC-V. It contains specifications, official documents, and updates about ongoing research and industrial adoption of RISC-V for our project. This resource helped us stay aligned with the latest standards and made sure that our implementation is consistent with the globally accepted practices of RISC-V community. The sixth one is Xilinx Vivado documentation. Since we used Vivado for functional verification of our processes, the official documentation of Vivado was crucial. It guided us through the steps of simulation, synthesis, debugging, and resource utilization analysis. Without these references, it would have been difficult to correctly configure our design environment and verify the correctness of our processes behavior before moving to the backend physical design. Thank you.
Good morning, sir. Today I am going to explain about our major project, the implementation and design of RISC-V architecture. So today I am going to show the output of entire single cycle RISC-V architecture. So these are the blocks which we are built this RISC-V architecture. So initially the number of blocks we built are add for PC plus ALU control, ALU decoder, data memory, extend instruction memory, decoder, mux for ALU source, mux for PC source, mux for register source, PC target, program counter, and register file. So I am going to explain these all code with the following. So initially I go move into the program counter. So I have opened the program counter file. So this is the design file in which we have defined the module and the input clock and reset, input PC underscore in, and the output as a reg. So we have defined it as a reg because after at always block the PC out has to be changed constantly. So if it want to change with a particular always block of POSIX clock, so we have to put the reg as a data type as output. So always at pause edge, even whenever the clock sets to positive edge, then this will change. PC out is set to PC in, PC, and else if the reset is not set to 1, then PC out is set to PC in plus 1. So now I will run the simulation. Yes, this is the simulation output what we got. So in this we have taken like for PC1 which is set to 0, for the positive clock cycle it is set to 4, and again if the PC in is set to 4, for the then again another positive cycle it is set to 8. So these are set like this. This is done by using the test bench. This is also which is written by us. So even the test bench is also similar to that of the design file, but here we have defined the module and the program counter, and the two data type variable reg and the wire PC out. So this is the instantiation block where we take the DUT, that is the design under test. So this program counter module is taken from the design file, module name program counter, and we inputted as the DUT. Then this is the instantiation block, and this is the always block where the clock should be rise and fall for another 5 seconds, and this is the initial block in which reset is set to 1 for PCN is equal to 32-H00, and reset is set to 0. It is set to H32-H004. So this is the block of the following. Again, this is the entire block. Now I will synthesize the now I will elaborate the design. Initially this is the elaborating step which we have to do. So it will generate the netlist. This is the reading the netlist. After generating the netlist, after simulation the netlist is generated. Then after generating the netlist, so we can see that after reading the netlist the design will get elaborated. Yes, we got the elaborated design. This is the elaborated design. After elaborating we have to run the schematic. So this is the schematic, and after synthesis, so we have to synthesize the design, so that after synthesizing we get the synthesized design by analyzing the power, area, and other delays, so we can compare the performance parameters. So yes, it was running, the synthesis design was running. Yes, it has become synthesis successfully completed. Now open synthesized design. So we have to open the synthesized design. Before opening, the other files elaborated design will get closed. So we got the synthesis design. So this is the device, and here the schematic is present. This is the schematic of the PC counter. So we can see many buffers and also the mux. So using these buffers and mux, the synthesis design are being generated. So this is the final. So by using this we should generate the bit stream, and we should open the hardware, so that we are using the RTX 7 board to show the output. This will be shown in the phase 2. So this is the entire process what we have done. Similarly we have done for entire blocks. So there are many blocks. Similarly, see, this is the entire block which we have. For these all blocks we have implemented the Verilog code design file and the test bench, and we have simulated it and elaborated the design. After elaborating we have synthesized the design. After this entire block will be uninstantiated with the same file for CPU, and after giving the input, so after giving the test bench, writing the test bench, we will get some sort of output. So this gives the only synthesized design, sorry, single cycle RISC-V architecture. So now I am going to explain the same RISC-V processor in the cadence tool. So here the RISC-V design file, and here is the test bench file. So I have named the design file as RISC-V.v and the test bench file as RISC-V underscore tb.v. So now we can see the design file. I am opening the design file. So this is the design file of the RISC-V processor. So here we have included the program counter. The logic of this program counter is nothing but initially a 32-bit B0 is set, then PC in is set, then after this PC adder is set, in which this PC adder is added with 4. It is added with 4 because so we have to implement a new instruction is to be added to the PC counter. So the instruction is of 32 bits. So here plus 4 is added, so that 4 8s are is equal to 32. So 32 bits forward will be made, and this PC counter, that is 2:1 counter. Normally these counters, these PC mux are used, so that under the following we have to prioritize the following. And here we are using the instruction memory. So this is the instruction memory where the entire instruction which is to be set is to be set. So here we can see the R type instruction and the I type instruction and the L type instruction, S type instruction, P type and U type, H type. R type stands for add, subtract, and or XOR, and set greater than, less than, left shift, right shift. And here I types instruction is set for immediate instruction, add I, or I, XOR I, and I. And this is the load type instruction, and this is the store type instruction, this is the branch type instruction, and this is the jump type instruction. This is the instruction memory register file. In this register file we can see the 32 registers in which random values are being held. So these, using these registers we will perform the operation in these counters, so that we will get the answer. Now the main control unit. So okay, 1 minute. This is the main control unit, in which so we have been a instruction set in which each of the ALU source and mem to reg, mem read and read memory branch ALU unit. These are the control symbols in which controls the each of the blocks. So we can see in this 1 minute, we can see in this major project. Yes, we can see in this, we can see in this picture, like this is the control unit where controls all the blocks. So this control units is the main region where all the blocks will perform its own operation as it required. The working will be explained by my friends. So these control units coordinates the following. This is the immediate block, where if the immediate is always a 16-bit or 12-bit, so we have to extend it to 32 bits. So we have added a 20 tick instruction 31, that is the uppermost bit is repeated 20 times, so that to add the 12 bit is extended to 32 bit. Similarly for all the instruction we will do the same thing. And this is the ALU unit, in which for a particular ALU control input we have to perform add, subtract and XOR input, like left shift, right shift, arithmetic shift. And this is the ALU control. By using the ALU op function 7 function 3 we have to perform the particular operation of the ALU control. This ALU out is set to in this ALU in. So in this formation, in this ALU control and this ALU, the operations will get performed. Here is the ALU mux, where to decide what to do, and is the data memory. Data memory is the defined memory where all the registers data will get stored or written back. So this is the data memory register, in which where again the mux logic same will be implemented. And this is the branch adder, and this is the RISC-V top, where entire block will be instantiated using this following. So this is the instantaneous block. So in this block it is given many wires are taken, so that internal connection has to be specified. This internal connection has to be specified, so entire is to be set. Now let's see the test bench file. So this is the test bench file. So it is a common normal file where the clock is set to 0, after 50 seconds clock is set to toggle, and reset is set to 1, after 50 reset is set to 0. So it is finished after 5200 seconds, and the file is dumped into waveform.vcd. So we should close the file. Now I will run the file. I will run this RISC-V processor. So while running, we have to do nc launch new, multiple step, create directory, save, yes, okay, sorry, directory, save, yes, do not include any libraries, okay. Now we got there. So we have to first initially select the file and launch the Verilog compiler, and also we should select the test bench file and launch the Verilog, and we have to select each and every file which is present in the modules. So these files are again set to launch elaborator so that it will be launched quickly. Instruction memory and mux, and again mux, and again RISC-V dot underscore db, and again RISC dot top, and again the register file, and again the immediate generator, and again main control unit, again PC adder, again PC mux, again program counter. Here we will obtain this block. So this the test bench file is then simulated, launch simulator. Now we will get the required output, that is the waveform that is to be generated. Yes, so this is the design browser in which we can see by pressing this plus, just by pressing this we can obtain the other DOT files. Yes, this is the DOT file. So again pressing this, these are the different modules which we have been created, and these are the design files which we are present. So these design files has to be sent to the waveform window. Initially this instruction memory has to be sent to the waveform window, and then this reg file has to be sent to the waveform window, and next this PC has to be sent to the waveform window, and this immediate has to be sent to the waveform window. Initially we don't require, we initially want to see the output whether it was working correctly. So we will take the first three instructions. So we will just minimize the other files. So we don't require this, and even we don't require this. So what we really required is the waveform window, and this is the file, that is the design file which we are required. So okay, I just opened this design file. So I'm going into that instruction memory so that how the instruction will be performed. Let's see only one simple instruction, how it is get performed and how it is get viewed. So I will run the file. Yes, we got the output for the entire RISC-V processor. Hence we got it. So I just want to minimize it little bit. Yes, so now we can see that this is the 1 minute. So we should just convert it into decimal, and we will zoom it so that it will be visible good. And this is the RS2, that is the register 2, even this is also, and this is the write register. So this is also converted to decimal, and this is the read data, where the data of the register will be stored in this, and this is the read data, where data of the register will be again stored in this. This is the write data, where the total value will be stored in this, and this is the register numbers, where which register has to be stored, and this is the destination register, and this is the destination register. Okay, now we can do the analysis. So now we can see this is the instruction memory, where the first instruction is add x13, x16, x25. So we have to add x16 and x25. So the register 1, this is the x16, so we can see the 16 number here, and this is the x2, rs2 is the x25, this is the register number. So this x16 and x25 has to be added to get that is the added number to that is stored into the register x13. See, we can see rd as a x13 register. So this is the instruction set which we have been given. Now this r1 has a value, we can see in this register file. So that in this yeah, 16, the register number 16 is 40. So the read data number 1, where it is 40 is stored. For this 25, so here it is 25, 65 is stored is here, this read data is stored with 65. Now stored with 65. Now we contain the write data, that is nothing but rd, which contains the 13. So this rd has write data where the output, so we have to add this 40 plus 65. So 40 plus 55, 105. This write data is stored with 105. So the instruction which I have inputted in the instruction file with the registers, it has performed the operation correctly and given the output as we want. In this similar type, this entire instruction which I have given will be get executed in this manner. So each and everything will be clear. So but in this red indicates that it is a don't care statement. So there is a small which is for single cycle we do not have any memory. So there is a small problem in this single cycle, because when it compared to pipeline, it requires latches, so it requires extra memory. But here we are not having any extra memories, so we are defining it as a single cycle. So entire process is one in run cycle, and the time required for to run is very large, but in pipeline it is very small. So now we have completed our execution using the single cycle. So our next aim or next goal is to do it the similar analysis using the pipeline architecture. Thank you, sir.